Okay, everybody. So now we are jumping into Unit 9 proper. Our states are phases of matter. Anybody remember what the 3 phases of matter are? There's 3 of them. Liquid's one, solid's another one, and gas are 3 main phases of matter, right? Well, here's the thing. In chemistry, it's good to know that something's a solid, something's a liquid, something's a gas. But the key thing is that in chemistry, we think only on the particle level. What are the atoms and molecules are doing with each other? And to help us see what's going on here, we're going to follow this little quick link. Everything okay back there? Okay. So first thing I want to do is I want to kick things over the water. Now, I see my water molecules and they're all hanging out in one place. For the most part, they're not moving around a lot, right? They're not spinning, they're not bouncing off each other. There are 3 main things that are going to determine whether or not what phase something's in. The temperature, the pressure, and how the molecules interact with each other. Those intramolecular forces, those IMFs that we talked about all the way back in Unit 4 when we talked about Lewis diagrams. Now, there's a couple things that we got to look at here. One, if we're looking at a thermometer here, my thermometer says 146 Kelvin. Has anyone used degrees Kelvin before? No. Usually what we see on a regular basis is Fahrenheit, or if you leave the country, you may see things in Celsius. So either as degrees F, degrees C, but here I got degrees F. Now I'm going to show you guys a little bit later how to calculate degrees Kelvin. But 146 degrees Kelvin is 127 degrees Celsius. If I'm dealing with water, what state of matter is my water? Is it a solid, a liquid, or a gas? It's a liquid, right? Because Celsius is all around a scale built around water, right? At 0 degrees Celsius, water freezes, yes? At 100 degrees Celsius, water boils. So if I'm at negative 127 degrees Celsius, why are my molecules moving? Because nothing's ever stationary. Our molecules are constantly moving. Now we may look at some of our molecules. This molecule right here, not moving around a lot, pretty stationary. But if I look something down here, I see them vibrating pretty strong, right? We are going to see that temperature has to do with what the particles are doing. The more my particles are moving, the higher the temperature it is. So right now, I'm in a solid state. So I got some ice right here. But you know what? Let's heat it up a little bit. I take my little scroll here, push it up. Got some flames boiling. Ooh, watch as my stuff's just cranking up. So let's see where we're at. 300 degrees Kelvin. All right. So at 347 degrees Kelvin, also 73 degrees Celsius, what state of matter am I working with if I'm looking at water? I'm 7 degrees Celsius, 73 degrees Celsius, and I know 100's boiling. What state of matter is my water in right now? Is it a solid, a liquid, or a gas? It's a liquid. With more heat, it'll eventually start to evaporate by itself, right? Notice that with my molecules is that some of them are spinning pretty quickly, some of them are not. They're having more interactions, they're reacting well with each other, they're bouncing off of each other. Remember what I said, temperature is just the average movement of my particles, also known as my kinetic energy. Now, if I crank this temperature up even more, let's keep this party rolling. They're boiling away. So 184, I'm at 211 degrees Celsius. What state is my matter in right now? My water. Is it a solid, liquid, or a gas? Gas. Some of my particles look like they've been doing drugs. They are spinning incredibly fast. Some of my molecules look like they're doing the opposites of drugs, where they're barely even moving. Remember, my temperature is just the average of these of the motion of my molecules, the average of my kinetic energy. Now, how this ties into the other two things that determine what state of matter is in. The faster my molecules move, the less likely they're able to interact with other molecules. When I had them frozen, I crank my temperature down. My molecules are interacting with each other. They're stacking on top of each other. What we're going to see, so we know, remember our IMFs, we took one of the strongest IMFs was our hydrogen bonding. The white circles are my hydrogens, the red circles, white is hydrogen, red is oxygen. Notice how they're interacting with each other. My hydrogen points towards my oxygen. I'm forming those hydrogen bonds with each other. The more interactions I have at a molecular level, the more likely I'm dealing with a solid. The less interactions I have, it's going to be a liquid. If they're having little to no interactions with each other, I'm looking at a gas. So let's break down our three states of matter based off of their interactions. Now, when we say solid, close particles with strong attractive forces. Now, when I say strong attractive forces, of course, I can't write on the board to make this easy, so I gotta swap over to my camera real fast so we can write this down. What am I talking about? I am talking about those IMFs, those intramolecular forces. Those are my London dispersion, my dipole reactions, and also my hydrogen bonding. These are the three main types of IMFs that we talked about in Unit 4. Now, if we remember correctly, London dispersion, spontaneous induced dipole, was the weakest of the three that we talked about. All molecules go through the London dispersion. Dipole only occurs with polar atoms. Hydrogen bonding only form when there's a very strong electronegative element like oxygen or fluorine attached to something that's not, like hydrogen. It allows for that interaction of a neighboring hydrogen to a neighboring oxygen or fluorine. But these were the three IMFs that we talked about. So solid has close particles with those strong IMFs. Liquids, they're close, but they have weaker attractions to each other. They're interacting with each other, but they're not very strong with that interaction. Yes, I do. And lastly, I have my gases. particles that are incredibly far apart from each other and have little to no attractive forces to each other. They're moving randomly. Three things are going to govern whether something is a solid, liquid, or gas. Temperature, pressure within the system, and the IMFs. Now, I'm looking at two hydrocarbons. I see carbon dioxide and I see ethanol used in cleaning. Adults drink it in order to gain effects that affect their brain. Which one is a gas at room temp? Is it carbon dioxide or ethanol? Yeah, carbon dioxide is going to be the one that's going to be a gas, right? Why? Why is only carbon dioxide a gas? Ethanol, I mean, it's got pretty much everything that that our buddy carbon dioxide has. That's fine. What makes it not a gas at room temperature? That OH group. Because of that OH group, my good buddy ethanol is a polar molecule. So that means that it has several interactions that's doing. It's doing dipole-dipole. It's doing London. It's also doing, because that's an OH, hydrogen bonding. My carbon dioxide is my carbon dioxide molecule just by looking at it. Can we tell whether or not it's polar or non-polar? Might help us out if we draw it out. Is carbon dioxide polar or non-polar just by looking at it? What do you think? Is carbon dioxide polar or non-polar? Katie? Charger for Katie? I should be able to see, because carbon dioxide is symmetrical, means if I split it in half, I get the same thing on both sides, it's non-polar. Meaning it's not going to have a lot of interactions with other things. Remember, a gas have little to no interactions with each other. The molecules are far apart because they're not attracted towards each other. They're moving around randomly. A lot of space for the carbon dioxide to move. By knowing a little bit about the molecule, I can tell what state it's going to be in at any given spot. Now, this is something I'd like for you to write down on your paper. I have a diagram at the bottom of your page. You are going to want to know these 6 placements. These, ladies and gentlemen, this is your phase diagram. Now, 4 of these you should be absolutely familiar with. You should know that if I'm going from a solid to a liquid, I'm melting. If I'm going from a liquid to a solid, I'm freezing. Everyone in here either took earth science or biology last year. So when I hit you with condensation and evaporating, you should be aware if something's evaporating, it's going from a liquid to a gas, and it will condensate if it's going from a gas to a liquid. Because remember, in the water cycle, bodies of water evaporate, the water molecules become a gas, they float into the atmosphere, where it's cooler in the upper parts of our atmosphere, where it condenses back down into water droplets. What you may not be 110% familiar with, deposition, sublimation. Has anyone ever seen dry ice before? You can get giant blocks of nitrogen gas frozen. Nitrogen gas, when it begins to thaw, it goes straight from a solid to a gas. It completely skips the liquid state. It sublimates. Disposition is when I'm going from my steam to my solid. Now, like I said, you should know these four pretty well. These two are going to be a little bit of a tricky one to add. But make sure you have your different phase names written on your paper. I'm trying to think off the top of my head. Let me take a look. So I don't know one off the top of my head. Oh, wow, that hit me hard. Frost formation. During the winter, it gets incredibly cold. And here's the thing, is that glass is typically colder than the air around it. Because of this huge degree change, water can skip straight from a vapor in the air to the frozen ice on your windshield of your car that you will go outside and scrape and be like, man, this really is annoying. Key thing to help with that, guys, is to start the car up, turn on the defrost, let it sit for a minute, then go scrape your ice off your windshield. Heat up that glass, makes it a little bit easier. All right, so I already mentioned what these three factors are. We're going to walk through each one. Our key factors were temperature, pressure, and those intramolecular forces. So we're going to walk through each one together. The first one is temperature. Temperature is the measure of the average kinetic energy of a particle. Now, when I say kinetic energy, what do you think of when you think kinetic? Things moving around. My kinetic energy is just the movement average kinetic energy. That kinetic energy is my energy from motion. Typically, we're going to talk about two types of energy. Especially when you get to physics, we're talking about potential energy, we're talking about kinetic energy. But if we're thinking kinetic energy, that's the energy that's used in order to move around. Potential energy is the energy that's stored within something. Fun fact, when I get to the coldest I can possibly get, which is absolute zero, the coldest theoretically, there is no more kinetic energy. Sir, just go back. Give me one quick second. Absolute zero is 0 Kelvin or negative 273 degrees Celsius. That is absolute zero. The coldest something could possibly be, theoretically, is 0 degrees Kelvin. Temperature is my first one. I have a quick little video to express temperature real fast. We'll do a quick little video. Shengeng, homework's online. It's an exit ticket.
Thank you.
So, let's watch a quick video. It's going to take about 4 minutes. And we're going to be wrapping up things for us here soon.
The humble thermometer. Whether we want to know if our holiday turkey is cooked, or if we need concrete proof we're too sick to attend school, a thermometer is the exact scientific tool we need. But what exactly does a thermometer measure? In other words, what is temperature? Really?
Whether it's solid, liquid, or gas, all matter is made up of atoms and molecules. These particles are constantly in motion. They collide with each other and with the walls of anything they are contained in. We quantify the motions of the particles by their kinetic energies. In chemistry, we define temperature of a substance as the average kinetic energy of all the atoms or molecules of that substance. Not all of the particles of a substance have the same kinetic energy. At any given time, the kinetic energies of the particles can be represented by a distribution.
Now, I'm going to turn on light because I do want you to record this graph. Now, here's the thing. This is what we would consider. Who's in algebra 2 right now? Anybody in algebra 2? Got one hand, got two hands. This would be a graph representing normal distribution. When we were looking at our molecules, they were all not moving the same speed, right? Some of them were moving very quickly, spinning, jumping around from place to place. Their energy is on the far right-hand side of my graph. Some of them weren't moving at all. We would find them on the, your far left. The items that were not moving very much are going to be on my far right of my graph. Remember, when we're talking about temperature, it's the average kinetic energy. So one thing we see on our y-axis, that's our number of atoms or molecules. Excuse me. On the bottom, what's my x-axis do you think it's going to be? You can't see it because unfortunately my bar is blocking it. Not time. My x-axis is kinetic energy. I'd like for you to draw this. I'd like for you to have this as a reference. I have a spot on the back of your notes that you can totally do this on. I'm also recording this so you can go back and reference it again. Because what will happen over time, if this is a normal distribution of the kinetic energy of water, we're going to see how a puddle can evaporate at room temperature. And it all comes down to this normal distribution.
Some atoms or molecules have a lot of kinetic energy and move very fast. Other atoms or molecules have a little kinetic energy and move very slow. It is the average kinetic energy of the particles that the thermometers measure and we record as temperature. One process that illustrates varying kinetic energies particularly well is evaporation. As you probably already know, evaporation is a phase change where particles of a substance move from the liquid phase into the gas phase. But have you ever wondered how a puddle of water can evaporate at room temperature? Keep that in mind. We'll come back to that question in a bit.
When we think about a phase change from liquid to gas, we often think about adding thermal energy to a liquid by heating it up. When we do, the molecules of the liquid move faster and spread slightly farther apart until they acquire enough energy to overcome the attractions they have for the other molecules of the liquid, and then they enter the gas phase. Think about this. If someone asked you to turn a beaker full of water into water vapor, what would you do? Well, being the brilliant young scientist that you are, you might put it on a hot plate and crank up the heat. Now, you can kick back and relax until the hot plate transfers enough energy to get all the water molecules to transition from the liquid phase to the gas phase. In less sciencey terms, you would boil the water. Boiling is a special example of liquid to gas phase change that occurs at a specific temperature called the boiling point, where the vapor pressure of the substance is equal to 1 atmosphere pressure. Boiling is usually carried out using a continuous input of energy from an external source, like a hot plate, to keep the temperature constant. The obvious conclusion is this. If you continuously add thermal energy from a hot plate, you can cause a phase change from liquid to gas. So back to the question, how can a puddle of water evaporate at room temperature? Well, during evaporation at room temperature, some fast-moving, highly energetic molecules have enough energy to overcome the attractions that individual molecules have for one another, and those high-energy molecules then enter the gas phase. As these high-energy molecules leave the liquid phase for the gas phase, the average energy of the remaining liquid molecules is lowered, and their temperature decreases. Because the liquid is now at a lower temperature than its surroundings, it absorbs energy from those surroundings, and the cycle continues as the puddle slowly evaporates. Boiling is a faster process because the surroundings, in this case the hot plate, heat the liquid to a higher temperature, where more molecules have high energy, so vaporization is faster. The hot plate is hotter than the liquid, so thermal energy transfer is fast enough to keep the liquid temperature constant at the boiling temperature. Evaporation can take place at any temperature because some of the molecules in the liquid, the ones at the higher end of the temperature distribution, will always have enough energy to enter the gas phase. To sum up, temperature represents the average kinetic energy of the particles of a substance. But it's the spread of kinetic energies among the individual particles that explains why puddles dry up.
All right, light on in 3, 2, 1. Let's go jump back into what we're doing. So, second to last one that we're going to talk about Phases of matter. Pressure. Pressure is number 2. If number 1 was temperature, number 2 is pressure. The force applied over an area. This represents the total impact of gas particles colliding with something. At standard atmospheric pressure, every square inch of you is being pushed upon inwards 14.2 psi, or pounds per square inch. The air is pushing down on you every direction, every square inch. So if you take the end of your thumb, put it on one side, that's one side of my square. If I do it, make a triangle out of it, connect it into a square, that's my square inch. Every square inch of you is being pushed down on by 14.2 pounds of pressure. Now here's the thing. The closer I get to the core of this planet, the higher the pressure is. We all saw what we saw the the reenactment of the Ocean View submarine that at a depth of around 1,200 feet underwater, crushed in the span of less than a second. Why? Because the force of pressure further was higher underwater than it is on land. The further I get away from the surface of the planet, my pressure, the lower my atmosphere pressure is. My last one, intramolecular forces. This is my third factor. That's the attraction between my particles, whether it be atoms, whether it be molecules, whether it be formula units. The weaker my interaction are, the less energy needs to separate my molecules. So it means that the weaker it is, the more likely it's a gas. The stronger my interactions, the more likely we're looking at a solid. Solids require more energy to separate the atoms than something in a liquid form. Solids require a lot more energy to separate the atoms than something in a gaseous form. Next class, we're going to see who is the strongest of us all. As I have a nice little demonstration that we're going to do, and we'll give everyone a chance to try to break my sphere. Don't worry, you'll see it next time. But also remember your types, your 3 types of IMFs that we talked about. Before I forget about them, go ahead and write them down. That was our, come on. Oh. Find a blank one. There we go. Our 3 types of IMFs. 3 IMFs. London dispersion. Followed by dipole-dipole. followed by hydrogen bonding. Strongest, weakest. Your homework for tonight, ladies and gentlemen, is a quick one. If you make your way over to our Schoology page, there you will find the homework pressure video and exit ticket. It's 10 points. Watch the video, answer the questions, and that's it. You're in, you're out, you're done. 10 points. Couple things I want to add. Next time I see you guys, we're going to talk about vapor and atomic pressure. Because there's some inequalities that we're going to have to pick up along the way for us to understand what's going on when we get into, excuse me, our different ideal gas laws. Now, I do want to point out a couple things. Quick reminders.